Hi, welcome to part 2 of first derivative test. Now in the last video we ended up discussing about how we can use the sign test to determine where a function is increasing, decreasing, where we have relative max and relative min. Don't forget the justifications. Now the one thing we are looking for is make sure you have a little sign chart or a way to beat so we can tell how you got your answer. So let's go and take a look at number 2. Now number 2, if you notice, we're getting a little bit triggylicious with it. So we know we're going to have to find the critical numbers, so we first start by taking the derivative. So remember, we are looking for where the function's increasing, decreasing, relative maximums, and relative minimums. And anytime we think of those, we have to think derivatives, f prime of x. And that's what we're going to start off with. We're going to take the derivative, which is, of course, this 1/2 minus cosine of x. Looking for your critical numbers, 1, where does the derivative equal 0? Or where does the derivative not exist? Now again, this is a sine function, so nowhere does it not exist, so we're not going to worry about that. But where does this equal 0? Well, we can kind of solve that. We get cosine of x equals 1/2. And you should remember from your trig, cosine of x is equal to 1/2 at pi over 3 and 5 pi over 3. When we do our sign chart, just like we did in the first one, now this time we do have a domain restriction. Over here we did not. That's where we got negative infinity. But over here we're starting at 0 and we're ending at 2 pi. Pretty much anytime we have a trig function, there'll be a domain restriction. Because remember, trigs just go up and down forever and ever and ever. So on top, remember, we're looking at the derivative. Please make sure, and again, you label these. Later on, these are going to become different. Next videos, we're talking about the second derivative. After that, this could become velocity, it could become position, acceleration. So this top part is going to mean something for us. And our derivative is 1/2 minus, of course, the cosine of x. And how does it make my function look on the bottom? So we're basically what the sign chart is doing is saying, here's my derivative, what does it make my function look like? For example, over here, when the slope was positive, it told me the function's going up, like a disco duck. Alright, so I'm going to label up my critical numbers, pi over 3 and 5 pi over 3, not drawn to scale. Now the nice thing about trigs tend to alternate, so if you can get one of these, you can get pretty much all of them. So if I pick something like pi over 6, and I take 1/2 minus pi over 6, so it'll be 1/2 minus, and I can zoom in here so we can see that a little bit better here. So again, this becomes then 1/2 minus root 3 over 2. Well, I know that's going to be negative. So between 0 and pi over 3, it's going down. And because trig functions, think about what trig functions do. They tend to alternate signs in terms of their slope. Go up, down, up, down, up, down. If this side is negative, this side must be positive. Goes up. Now there are cases where it won't alternate, but that's dealing with multiplicity. We'll see examples like that soon enough. Over here it's negative, so it goes down like a disco clown. And now I can write my answers. Let me zoom out of here. So we know this function is now increasing on the domain pi over 3 to 5 pi over 3. Now if you notice, we're always using a soft bracket. That's because at pi over 3 and 5 pi over 3, it's not increasing or decreasing. These are where the slope is 0. So we cannot include those. And this is, of course, because our derivative is positive, greater than 0. We are decreasing on the domains 0 to pi over 3, or 5 pi over 3 to 2 pi. And that's because the derivative is less than 0. We have a relative max at x equals, where does the slope go up and down, 5 pi over 3. And that is because the derivative goes from positive to negative. And there is a relative minimum at x equals, where does the slope go from down to up, pi over 3. And this is because the derivative goes from negative to positive. Very easy to do. All told, a question like this is maybe a couple of minutes, 2-3 minutes. Oh no! Look at this one, number 3. It's got a fraction on it. Alright, so let's see here. If we were to take we know we're going to find the derivative, so we need our critical numbers, so we take the derivative. And I'm going to use again quotient rule. Don't use product rule. Don't make that a power. That becomes really ugly. Low plus 1 d high minus the top times the derivative of the bottom, all over the bottom squared. It's not too bad because this cleans up decently at least. We're going to get 2x cubed minus 2x cubed, so those cancel. So on top we get 2x, and on bottom we get this x squared plus 1 squared. And there's your derivative. Finding out your critical numbers, where does the derivative equal 0, or where does the derivative not exist? Well, again, we know this from before. We're looking at the top from where the slope is 0. So 2x equals 0, so x, of course, equals 0. There's one critical number. And then we look at the bottom, right? To find out where the derivative does not exist, we just look at the bottom. And that gives me x squared plus 1 squared equal to 0. And if you notice, you can't solve this. That's imaginary. Okay? Don't make this problem any more complex than it really is. So we don't worry about those. Okay, so we can't solve that. So my one critical number is just 0. So let's see what this looks like. Interesting. 0 is my one critical number. I don't have any domain restrictions like we had up here. So the sky's the limit. So again, on top we'll put the derivative, which is our 2x over x squared plus 1 squared. And the bottom, it's how does my function look? So I pick a number less than 1. So I'll pick less than 0, so negative 1. If I plug that on the top, I get a negative. The bottom, because I'm squaring, will always be positive. So this is a negative slope, so it goes down before 0. If I pick a value after 0, like 1, the top, 2 times 1 is positive. The bottom, again, no matter what I put in, it's going to be positive, and it becomes a positive value. Now, every year somebody said, but what if the bottom's 0? It won't happen because we just showed that it could not occur. So, this is an interesting graph, by the way. We can actually kind of graph this. At x equals 0, we have our point. Before, we know the slope is negative, and afterwards, we know the slope is positive. Using our limits, if we take the limit as x goes to infinity of our function, we're going to get 1. That's the big on top. And the ratio the same. So there's 1. There's my horizontal asymptote. So it kind of looks like this. This is what the graph kind of looks like right there. Alright, but anyways, that we digress. So we answer the question, where is this increasing? We are increasing on the domain 0 to infinity. It goes to 0 slope eventually, like if we go forever, but it will always still increase. And this is, of course, because the derivative is greater than 0. Where is this function decreasing? Well, on the domain negative infinity to 0, and that is because the derivative is less than 0. Do we have a relative max? None. And that is because the derivative never changes. The derivative never changes from positive to negative. Is there a relative min? Yeah, absolutely. At x equals 0. Now, speaking of absolutely, remember, these are not our absolute max and mins. That you need candidates test for. This is just called the sign test. This is only test for relative max and mins. So we have relative minimum at x equals 0, and that is because the derivative goes from negative to positive. From negative to positive. Now, sometimes people say, but Mr. Werner, isn't that a cusp? Yes, it is a cusp in this situation, but remember, critical numbers are defined by slope of 0 or does not exist. As long as it's not asymptotic or an endpoint, it's still a minimum point for a graph. So that's why this is still considered a relative minimum here. All right, for number 4, we talked about this before. This is absolute value, and we always sketch absolute value. Always sketch absolute value. So when I graph this one, we should know what this looks like. It has a vertex at -3, down 1, and this opens up like a disco duck. Not drawn to scale, our favorite phrase in mathematics. So this time to get my critical numbers, I don't really need to do the derivative. I can just look at my graph. Where does the derivative equal 0? Nowhere. It's a corner right there. So that's not a 0 slope. Where does the derivative not exist? X equals -3, where the corner is located. So when I do my sign chart, I'm going to do the same thing. I just do it. F prime and F. F prime, remember, this is dealing with the slope of the graph. And before -3, what can you tell me about the slope? Of course, it's going down. It's negative. And after -3, it's a positive slope, so it's going up like a disco duck. And I'm going to answer the questions just like I would normally. This is increasing on the domain, -3 to infinity, and that is because the derivative is greater than 0. This is decreasing on the domain, -infinity to -3, and that's because the derivative is less than 0. Is there a relative max? The answer, none, because there is no change from positive to negative. Remember, we can even look at the graph. There is no relative maximum value. Is there a relative minimum? Yes, it is at x equals -3, and that is because the slope, or the derivative, goes from negative to positive. Okay, now sometimes people wonder, why do we still show our sign chart? I show my sign chart because it's the habit. The AP likes to see your work, the justification. Show that you know, in other words. And this kind of shows that you know something. So I would still suggest you show this, even though we can get the answer from our graph. Because we won't always be able to see the graph. We always look at we always get our work from here. We get our answers from our sign chart. And that's what we've done from every single one of these. I know this is decreasing on -infinity to 0 because my sign chart shows me going down. I know that I don't know what this graph looks like right here, but I know between pi/3 and 5/3 the function is going up. We get our answers from that sign chart. Anyways, I hope you enjoyed the videos. I've enjoyed making these so far, so I will see you guys next time when we discuss concavity. No, we're not going to the dentist. See you then.